Okay, we're continuing our discussion of interaction diagrams. Remember that an interaction diagram is a collection of every combination of P and M that would cause failure. One thing I forgot to mention last time, you can see that there are, I believe, 8 different lines there, 8 different interaction diagrams. What they correspond to is a percentage of steel in your column. This smallest one on the inside, oh, that smallest one on the inside is 1% steel in the column, and this largest one on the outside, that's 8% steel in the column. And so it's convenient. On one graph, you have 1 through 8% steel, and that represents the typical range of steel in a column. In fact, I believe 1% is the minimum allowed and 8% is the maximum. Now let's talk about the effective shape of your column. Okay, here are the 3 types I talked to you about. Round, let me get that there. Square with steel on all 4 sides, and square with steel only on 2 faces. And you can see that the most effective is to put, and they're therefore equal percentage of steel. And so the most effective in terms of moment is to put all the steel as far away from the middle as possible. So it'll be the one with steel on only 2 faces. So that has the highest moment capacity. Remember, the x-axis is moment, but and then the one with steel on all 4 sides but square has the second most steel farthest away from the neutral axis. Okay, so what I'm talking about is this. That distance away from the neutral axis, the percentage of steel, you can see in that one, all the steel is on the 2 outer edges. In this next one, 6 out of the 8 bars, and remember it's equal amount of percentage steel, so only 6/8 of the steel is far away. And in the circular one, only those 2 are really far away from the neutral axis, and that one has the least moment capacity. And but the other thing is that these are all the same height, and I believe, was it? Let me. No, I think they were equal area. So they're equal area. So the more efficient use of area is a circle, and so you can see that the highest axial capacity for the same amount of concrete, or is that one. That doesn't make sense. So why is that higher? Oh, it's because the round one is spirally bound, and so it has a lower max reduction. But the key thing is that for efficient moment capacity, uh, you can see the effect there. The next question is, what happens if you have, and this is beyond the scope of this class, what happens if you have moment in 2 directions? So this would be a column in the corner. So a corner column in a building is bending in both directions. And so what's its capacity? And what happens if you have 2 moments, the neutral axis is skewed, like in that picture, and then you use the same principles, and you can make a interaction diagram in 3D, okay, to do that. And the three axes are axial force, moment about the x-axis, moment about the y-axis, and then you get a surface, and any combination of those three that lands on a surface will cause failure. This is a pretty difficult problem, and when I was an undergraduate student, my honors thesis was actually to solve this problem, and so I made a computer program that would solve this. So I forgot what I did, was given any EX and EY, I could then tell you P, M, X, and MY. And it involved like a two-dimensional Newton-Raphson thing. Anyway, let's now just talk about, let me get this out of the way, some practical things. You're allowed to put 1 to 8% steel in a column. It doesn't sound like much, but you're not going to fit more than 4% steel if you're trying to put it on the four sides or around the perimeter of a circle. It's just not going to fit. So for placement, a practical amount of steel, even though you're allowed to go up to 8%, is 4%, and for economy, 2% and under. The minimum number of bars, it should go without saying that you need 4 if you have a rectangle, right? You need 1 in each corner to put that tie. But for a circle, for these spirals that are, let me get this, for the spirals, let's see if I can do this. I'm trying to make the pencil, see if I can make my finger go in a circle. I can't do it. It's harder than it looks. Anyway, the spiral, steel, you need 6 bars, okay? Minimum of 6 for circles. You have to tie these things, okay? Those ties, it's pretty easy calculation. It's not really a calculation. If the bars in your column are 10 or smaller, you use number 3. And if your bars are 11 or larger, use number 4. Okay. For beams, I did not let you use the 14s and 18s. I said 11 or smaller because the bars are just too heavy to be practically placed in a beam. Now is when you can use the large bars, the 14s and 18s. They go in columns. That's what they're for. And then the spacing of the the ties. Okay, so how far apart can you put these? Okay, it's the least of 16 times the diameter of the vertical, I call them the long bars or longitudinal bars. 48 times the diameter of the tie, which is going to be a number 3 or a number 4, or less than the minimum column thickness. Okay, so if you have a 12 by 18 inch column, 12. Okay. Now, this one here is particularly important. We didn't really understand that before 1973. These ties need to be spaced less than that because these bars are like miniature columns and they can buckle. If you put the bars too far apart, once the concrete comes off of the outside of the column, these bars can buckle. And if you've ever seen an earthquake and a collapsed building, you often see a picture that looks like this. you see the column crushed down, and you see the rebar just spitting out like that, like spaghetti. And that was probably built before 1973, before we had this requirement, and the ties are spaced too far apart, and then the column just buckles, and all the concrete comes, not the column, the long bars buckle, and then the column just collapses down like that. Okay, it's just something we didn't think about. Okay? If you have spirals, the minimum is 3/8 inch diameter, or number 3, and they pitch, the pitch of the spiral is 1 to 3 inches, and the percentage of steel for a spiral is the volume of the spiral steel divided by the volume of the concrete inside. And if you're good with geometry, the volume of the spiral, right, is one circle around. Okay, and it's slightly longer because it's a helix, but we're just going to say the spiral is about that long, pi times d, right, and times the area of the spiral. That's the volume of the spiral. Okay. The volume of the column in that spacing, right, is just the area, pi d squared over 4, times the height, the space, and there you go. Okay, so that's the volume. Okay, that's the ratio. Okay. Okay, we don't want the bars to buckle. That's why we're putting these ties. Okay. Those bars are not going to buckle. This bar can't buckle out, but it could buckle side to side, right? If this concrete comes out, if that concrete comes out right there, that bar, let me make it a different color. That light blue bar can buckle side to side. Okay. So if it's within 6 inches of a bar that can't buckle, we're going to say it's good. It's not going to buckle. Okay. So the distance from that bar, the space, that space needs to be less than 6 inches. Otherwise, it might buckle side to side. If it's more than 6 inches, you're going to have to do something like this. That light blue diamond there, it's now confining those 4 bars. So in dark blue, let me show you now all the bars that are safe from buckling. Those 8 bars are now safe. Okay. And so now the ones that I've not highlighted, if they're less than 6 inches away from their neighbors, then they're fine too. Okay, this is kind of a tricky thing to do, and if you have Dr. Dolan's book, he has a lot of pictures and recommendations on how to put these ties in. Okay. Okay, let's end all this with a quick example on how to do capacity, not how to do design. We'll have a separate video on how to do the design. And so this is just how to check the capacity of a column. Okay, let's say we have a 15 by 24 tied column. It's got 4 bars in it, and the total area of steel is 4.71 square inches. And I know the eccentricity, the ratio of M to P, is 1.2 inches, and another time it's 9.6 inches. Okay, and so I want to know the capacity when the eccentricity is small, and I want to know the capacity when the eccentricity is larger. Okay, and we're going to do this by using these graphs. Okay, so I've got a graph here that is, is it the right? It's the wrong gamma. I pasted in the wrong one. I wanted the one that was gamma is 0.7. Oh well. Because what I did was, first of all, you get the percentage of steel, and then gamma is the ratio of the distance between the steel. Okay, and so if you take 16 point, I forgot what it was, 24, so that distance between the steel is 16.8 divided by 24, the gamma is 0.7. Okay, so I have to find, so I put in the wrong one. I just did this. So I was supposed to find the plot for gamma's 0.7. And I was wondering why my calculations came out a little wrong. As the file name said 0.7, but it's the wrong one. Oh well. So there you go. So right here. I need to find gamma's 0.7. I gotta go dig through and find that interaction diagram. Anyway, I calculated gamma's 0.7 so I could go grab the right graph, which I didn't do. And so for E is 1.2 inches, E over H is 0.05. And then I read on the graph, or I fudged on the graph because it actually wasn't coming out right, that the y-axis was 0.83. And then from that, I solved for Pn. Let me show you what I did. So I went to this graph. Okay, I know that E divided by H is 0.05. So here's a blow up of what I did. This line right here is 0.05. And then I tried to find 1.3%. And I came over, and it actually looks like, to me, it looks like 0.84. But I said, oh, that's 0.83 because I had to, that's what I said I saw. I saw 0.83 in the slide. Because I made the slide doing it on paper, and then I pasted it in the wrong picture when I tried to do it on a computer. Anyway, so I get that the y-axis was 0.83, but I want to know Pn. I don't want to know Pn divided by F prime C times the area. Okay, so Pn is, so this is one of those graphs that has F prime C in the denominator. So Pn is 0.83. I just put everything on the right-hand side. Times 4 was F prime C, and the area was 24 by 50. Okay. And I think I got that wrong too. It's 24. Oh, it's 24 by 50. Okay. Problem number 2. Again, the 0.7 graph. I grabbed the wrong one. E over H is now 0.4. Okay. And it's still 1.3%. So I went on the same graph. That was the 0.4 line. And I just tried to interpolate. See this line here? Those are the 1 and 2% lines. And so all I tried to do on this purple line here, I just eyeballed 30% from the 1% line up to the 2% line. And I thought I saw this. I saw that point right there. And then I came across, and that doesn't quite look like 0.41. But I said, oh, that's 0.41, because I didn't want to change the slide. And so I said, oh, I saw 0.41, and I was wondering why the graph wasn't exactly matching what I had typed up. Maybe tomorrow during the Zoom session, I'll redo it with the correct graph. Anyway, 0.41 was what I read on the y-axis, and then again, I don't want 0.41. I want to know Pn, so I put the denominator over on the other side. I get 590 kips. So notice that when the eccentricity is small, you can hold 1200 kips, and when the eccentricity is high or the moment's high, it's like half of 0.59, 590 kips. The moment, you could try and read the x-axis off of those things, but it was easier since I know that the moment is just P times E and E was given. I just took what I got for P. In this case, 1,195 times 1.2 inches, which obviously I rigged because that's 0.1 feet. So it's 119.5 foot kips. Similarly here, if you take 9.6 over 12 is some nice number. I can't remember what it was. So if you take 590 kips and multiply by 9.6 over 12, you get 472.3 foot kips. Okay, this is a little esoteric. We will not use the diagrams like this. What we're going to use the diagrams for is for design. Okay, and here's the design procedure. But let me move myself. This is a design procedure, but that's a video for another day. Okay, so I was looking over the interaction diagram stuff that I did. And while this is the wrong picture, the one I actually took the readings off, that was the right picture. Okay, so I just pasted the wrong picture on this slide, but the one I actually did the tracing on was the correct one. So now I'm going to look at this more carefully. So let me zoom in and let's see how badly I cheated. Okay, because I know that the answers are supposed to be 0.83 and 0.41, and so this is the 0.4 line going up. And so what you need to decide if I cheated, okay, is this. Is this dot? Let me see. I have my iPad off, so I'm gonna try and do this with the mouse. So this might get ugly. Okay. So the question is this dot right here? Do you believe that that's 30% between there and there? And I don't know, that looks about 30%. And then the next thing is, as you come over this way, does that really look like 0.41? So actually, I was actually right. So that one's okay. The next thing is, okay, so if you look at this dot up here, I don't know how to, there's a way on PowerPoint where I'm supposed to be able to highlight, but I'm looking right here, okay? That dot to this dot, that's 1 to 2%. Remember we had 1.3%. Do you think this dot right here is 30% of the way between 1 and 2% on that purple line? And I think that's good. And then the next question is, when you come over here, yeah, that looks like 0.84, not 0.85, but I said it was 0.83 just because, to be honest, I was lazy. I didn't want to retype this slide. It's out of the screen. Oops. Oh, just so you know, this is how VidGrid works. It just puts a square on my computer screen, and I just have to put whatever I want to be recorded in there. So if I drag stuff around, that's just what it's going to record. It's kind of weird. So what I do is, before I start recording, I center that, and then I increase the slide until it fits the recording window. And I'm not actually running PowerPoint. What I'm really doing is I just got this going, and when I before you do present, and then I just click here to make the slides change over there, and that's what you're seeing in the little window here. Um, uh, all VidGrid does is capture a small window of what's on your computer screen, and that's what it's doing. But anyway, um, this was right. And then see, when you lie, you just catch yourself in all kinds of uh, um, problems. I anyway, I think that was good. The 4-1 is good. That 8-3 might have been 8-4, but so you can see this is not the most exact thing in the world. You're just using eyeballs. But this is not what we're going to use the interaction diagrams for. What we're really going to use them for is you come to the diagram, and from your loads, you know P and M, and you just plot P and M. So let me see if I can do that. I'm going to try. So you just plot your P and M on here, and if it falls in there, that means you need 3% steel. Well, depending on how good you're eyeballing in, you say I need 2.5% steel or something like that. That's what you use these interaction diagrams for, as design. You get the P and M off of your loads. You come to these things and you just plot them. You just plot it, and then you find the line that's outside of it, and that's how much percent steel you need. And it's even easier if you have a spreadsheet, and I'll show you how to use a spreadsheet in a separate video. And so I've got a spreadsheet that you type in all the dimensions of your columns, and it will draw your interaction diagram for you. You don't have to put denominators, F prime C's. It actually plots it in foot kips, or I think I do it inch kips and kips. And then you just look at the plot and then just see if your point is inside there. And the spreadsheet, it's made so that you can just change whatever you want. Like, I want my column to be 16 inches. You change it, and it changes the graph. And it just takes like 2-3 minutes to design a column. Okay, and of course, you'll have that spreadsheet for the exam. So there you go. But just to come back and say that that was the right graph. This one was not. I just pasted this wrong one in, but this one that I pasted in where I drew it, so I took the correct diagram, put it on my iPad, I drew on it, and then I put it back into PowerPoint. This was the right one. Okay, just wanted to update the video with that.